Hi everybody, I'm Karthik, one of the co-founders and the CTO at Yugabyte, and we're going to talk about distributed database architecture for GDPR. Okay, first off, a quick intro about us. The three of us founders at Yugabyte, we all worked at Facebook. Right before this, I was at Nutanix working on distributed storage, and about like a whole bunch of people in our company have a practical experience building databases such as Oracle, HBase, Cassandra, etc. Okay, so real quick recap on what YugabyteDB is, and we'll go right into the GDPR side of things. Yugabyte is a transactional planet-scale database for building high-performance cloud services. Yugabyte brings together SQL and NoSQL in a cloud-native fashion. Here are some of the design principles on which Yugabyte is built. It is transactional. It supports single shard and multi-row distributed ACID transactions. It has a document-based, strongly consistent core storage engine. It has high performance in the sense it offers low latency reads and can deal with high throughput reads and writes. It is planet scale, so it natively understands global data distribution and automatic sharding and rebalancing. It's built for the cloud native era, so it works with containers natively on Kubernetes. It is self-healing and fault tolerant. Yugabyte is also really good if you want to run it on bare metal or VMs in addition to containers. Finally, it's open source. The Yugabyte is on GitHub on the Apache 2.0 license, and it also extends open source API. So the good part is you don't really have to learn anything new in order to use Yugabyte. It uses Apache Cassandra, Redis, and Postgres compatible APIs. Okay, so the main topic now. What is GDPR? So let's start there. GDPR expands to General Data Protection Regulation. Okay? It is some control that the EU gives to European citizens, the citizens of the EU, on their personal data. So we're going to look at what control means, control with respect to sharing and protection of their data. So we'll dive deeper into control and what personal data means. So we'll start looking at these two in detail. Okay, so personal data is also often called PII, or personally identifiable information. It involves pieces of data that can identify who you are uniquely. This includes things like a username, an email address, a date of birth, bank details, your location details of where you live or where you're present at the moment, and a computer IP address. So these are just some examples. Now, what GDPR says is you need to give the citizens of Europe control over this personal data. So what is control? Well, there's two broad categories of control, and we're going to classify it into database concerns and application concerns. Now we're going to go into each of the database concerns in detail, but it's roughly around consent and data location, data privacy and safety, right to be forgotten, and data access on demand. But let's touch real quick on the application concerns. If there is a breach of a user's data, you would have to notify them. So you'd have to build this into the application on figuring out how to notify the user that their data has been breached. A second bit is a user can come and ask you to transfer their data from you to another operator providing a similar service. So you'd need to enable the end user to be able to do that. A user may come to you and say, hey, some piece of data you have about me is no longer correct or was incorrect always, and they would want it fixed. So you should be able to fix errors in data. And finally, you should be able to tell them what you're using the data for and restrict it. If they say, I don't want you to use it for all the purposes you're using it for, could you please stop using it for some things? You should be able to do that. So all of this relates to application concerns. But now let's go into the database concerns, because that's where the database architecture comes in. Okay, the first database concern is around user consent and data location. What does that mean? Data must be stored in the EU by default. So if you're dealing with a EU citizen, and they're living in the EU, you need to store their data in the EU. And businesses need explicit user consent to move the data outside the EU. Okay, so what's so hard about that? Well, firstly, the EU users' data lives in that region. Other users' data need not live in that region. But EU with GDPR is not the only geographic location that has a compliance regulation. There may be other countries that have equal or similar compliance regulations. So now you're talking about different subset of users' data living in different geographies. Now, following up right on its heels, the issue is that you may be using a public cloud like AWS or Google Cloud or Azure in order to store the user's data, but a single public cloud may not have full coverage for all the countries and regions that you have to store the data in. So that means you would have to go across multiple clouds, including some private clouds at certain points, and that points to hybrid deployments. Finally, your architecture actually now depends on the data. Your data for a single service may be PII or may not be PII, and your architecture of where you store that data, where you replicate it, how you use it, actually depends on the data subset, which makes it a little complicated to design such systems and services. So overall, the takeaway is, for the world you're operating in today, if you expect to have international customers, you need to think global deployments first. It can no longer be a second-order concern. Okay, let's take an example, right? So to make things much more clearer. Let's take an online e-commerce site that is selling some products to an international audience. Well, the first thing that they'd have in their service is a products table. The products table, however, needs global replication because it's not PII. It doesn't identify any user. So that means you would have to move your data closer to the user so that they can access it quickly, because one of the key requirements is to get people to browse your products quickly to make the site very interactive. But you would be okay to replicate the entirety of the data across the globe. And you can achieve that very easily with YugabyteDB's global replication. Now, you might want to disperse it further into even more geographies in order to achieve low read latencies from the end user, and you can do so with read replicas. Now, let's take some other pieces of data in the same e-commerce site. Now, there would be a notion of users because they may want to register with your site. They may want to purchase some products and place orders and track their shipments. Now, all of these pieces of data are PII. They identify a user because I ordered a product. This is me and it's my profile. A shipment is coming to my house or to my destination location, and all of this constitutes identifiable data. Now, there are other things like where is the product currently located, like in the shipment, like when it's being delivered to me, its actual geographic location. It may or may not be PII, and that depends on how the application is designed. So overall, there is a bunch of data, a subset of the data that is PII. Now, for these, you would need to geo-partition the data. You would need to keep the non-EU users' data in different localities. If there are other geographies that require regulatory compliance, you need to keep that user's data local. But for purposes of GDPR, you definitely need to keep the EU users' data in the EU, right? Now, so this sort of a design is also very easily enabled by a globally distributed database like Yugabyte. So let's go further. Now, let's say you asked some of your users and they are okay with replicating your data to other geographies. Now, if that happens, you would need to quickly know how to move this data to another geography in order to utilize it. Now, you could do something like set up a read replica for remote low latency access because users are okay giving you access to move this data out. You could do something like a change data capture where you go ahead and figure out what changes are happening to the data and you replicate that to a remote region. And you may want to bring all of the data in your entire store together for a single pane of glass to do analytics to figure out what products are popular, which regions are people have demand for which things, how much should I stock in my inventory, so on and so forth. Okay, so let's take a quick architecture diagram style look for the PII data. What you find is you have your primary data in the EU. If the user gives you consent, you can move and replicate this data globally using the read replica feature of YugabyteDB. Okay, let's go to the second concern, data privacy and safety. Once again, what is this requirement? Well, what it says is that data must be secured using best practices by default. And if there is a breach, the user needs to be notified. So what it says is you really need to do your best to protect the user's data. So that means it is best to think of the state of the art and just do state-of-the-art security practices on day one, as opposed to figuring out what to do on a breach, how to notify users, and to justify if all the efforts were taken to protect the data. Now, that means the best way to secure the data is to implement end-to-end encryption on day one. What is end-to-end encryption? It typically consists of two parts. You have network communication and you have data storage. So the first part is you need to encrypt all network communication. TLS encryption is commonly used in order to achieve this, and there are typically two network segments you can think of. There is the client to server interaction, and there is the intra-server or the replication between the databases. Obviously, both of these have to be secured. So let's take a quick look. In this diagram, if the user accesses a piece of data, that is the client to server communication piece. And it may be something where the user is writing data or reading data out. And specifically, in a distributed database, you may have to read data from one node which internally needs to read data from another, or you may write data to one node which needs to replicate data to other nodes. So there's server-to-server communication in order to replicate data and do remote reads. Now, both of these would have to be encrypted. Okay, the second bit we talked about is encryption at rest, which is required in order to encrypt every piece of data that the system stores. Now, the best way to achieve this is to integrate with an external key management system. Unlike the network piece, which is ephemeral or fleeting, you can always change network keys and restart your servers, and you will now have new communication that works. That is not the case with storage. Your data, if it is encrypted using a key and the key gets out in the wild, it is really difficult for you to re-encrypt your data. So it is important to think about how to rotate your keys, how to change the key after the fact. So it's typically good to design your database in order to do key rotation to work with an external key management system. So key rotation is very critical on demand. Now, there are other techniques that we are going to talk about in a subsequent section, which is to manually encrypt keys at the app side and store them. And there is a huge benefit for doing this as well, because in most of the automatically encrypted systems, the argument could be made that if you are able to break into the actual database, somebody could get the data decrypted using the database server itself, right? So this encryption at rest doesn't solve that use case, but we will talk about this more in a different section. Okay, how does encryption at rest look architecturally? Well, you have the user who has written some data. The data should be written to disk using encryption, and that encryption is performed by integrating with a key management system, and you are able to rotate keys. Okay, let's talk about the next requirement, which is the right to be forgotten. What does this mean? It's pretty simple in the ask, in spirit. It says, if a user deletes their data or requests their data to be deleted, you actually need to purge it. If you had been collecting data for a specific intent and your intent changes, you need to delete their data because you're no longer using it for the originally stated intent. So it's basically all around erasing the data and you having no access to that data anymore. Well, that's easily said, but it's much harder to implement and practice, especially when you have a lot of data, because deleting small bits of data and ensuring they're no longer present in disk is a non-trivial problem. So here's the same technique we talked about even for the encryption and security privacy part of thing, protecting user data section previously. So what you could do is to have a key value table which has a personally identifiable ID to a cipher key. So you have an ID of a user, you store a cipher key against it. every piece of PII that you store about the user, you should encrypt it using this encryption key when you do a write or an update. When you do a read, you would need to read this key, decrypt the value, and return it to the end user. Now, when the user wants you to forget their data, you simply delete the cipher key and don't worry about how many places this data has proliferated into. The advantage is you have some decrypted set of bytes, and that is no longer personally identifiable. So let's take a look at a real example, a workflow. So let's say that you have a user profile example, and there is a user trying to update their email, which effectively translates into a database query which says, set the email to a new email for a user ID that is something. Now, the first thing you would do is look up the encryption key for the user. You would then encrypt the PII portion of the data, which is the email address. Now, there could be other things that the user has, some preferences as to what is the font size they want to view their browser. And these are not PII, but specifically the email field is PII, and you encrypt it. You then store the encrypted value in your table. When you read it, you read the encrypted value, you get back your encryption key, you decrypt it, and serve the value. And if you simply delete the encryption key, the data is no longer accessible. Okay, so a slightly related but variant technique is to use anonymization of data attributes. Now, there are a number of cases where you don't actually need the attribute value. You just need an identifier. Like, you could do so, like in the previous example, if the user wanted to view his email, then you definitely need the value of that email. But if you are just tracking how many people have signed up on a particular day, or how active is a particular person 30 days after signing up, you just need a stable value, something that represents the user but not the actual email address. So in such cases, you can anonymize the PII data with a one-way hash function. And this is mostly for real-time analytics and data warehousing, where you can use the hashed IDs, which represent the user but don't give you any information about the user. Since this is not PII, you could treat the hashed IDs, the one-way hashed IDs, as regular data. Again, let's look at an example. Now, you want to store the fact that a particular user with some email checked out a product in some category. Now, we go ahead and do a one-way hash of the user ID or the user email, which is PII, and we now have a hashed value. Note that it doesn't matter how many times the same user buys a different product, we always get the same hashed value for their email, and we would never be able to guess their email from the hashed value, so it's not PII. Now, we can go ahead and put this information into the analytics cluster, and we would still be able to get all the analytics we want without being able to actually pinpoint which user that was. As an example, you could do pretty complicated things using a cluster like this, using this sort of information. Like, you could answer questions as to which of your categories are the largest contributors to your revenue, because you have all the hashed IDs that bought your product, and you'd be able to figure this out pretty quickly. So hashed data is still pretty useful. All right, let's go to the last item that we had wanted to talk about in distributed data architectures, which is data access on demand. What is it? Well, you need to tell the user about what their data is being used for, like which of their data attributes are you storing, what purpose are you storing it for, and where you're storing it. So they need to know what you're collecting about them, how you're using it, where you're storing it, all of those details. Well, the best way to achieve this, because in a massive deployment over time with new features being built, there's a sprawl of many databases, many columns, many attributes, and this becomes very hard to track. So the best way to do this is to be able to tag tables and columns as having PII data. So store this tagged information in a separate information architecture table, and make tagging a part of the development process. If a new feature is being developed, one of the key questions before it goes into production is for people to look at and tag data as PII or not PII. That way, it is very easy to locate which pieces of data are PII, where they're being stored, and what they're being used for. Now, there is another advantage to having this in order to truly enforce compliance. You can firstly run checks in the background periodically to ensure that the PII data is indeed encrypted. You can ensure also that the non-PII columns don't have sensitive information like an email or a date of birth or so on. And in order to achieve this, you can use an analytics system such as a Spark or a Presto to perform the scans periodically. And finally, a lot of people don't want their production clusters to take a hit. So you could create a read replica of the production cluster in order to keep scanning the data without impacting your production traffic. So let's look at this diagrammatically. Okay, so you have a cluster. This has some PII data. Well, the first thing you do every time you create or alter or modify a table is to tag columns as PII and tables that contain these columns as PII tables. The second thing you do is feed this data into a Spark or a Presto or some sort of a real-time analytics cluster. And the analytics cluster is going to go in periodically, read all the data out, and make sure that the PII columns are encrypted. The non-PII columns don't contain sensitive data. So let's put everything together. We talked about 4 independent items and the information and the database architecture you need to support those. So putting it all together, well, you first have a primary cluster, which has to be in the EU if it is PII data. Now, you would be getting encrypted reads and writes in order to ensure end-to-end encryption. You would, every time you create or alter a table, tag the PII columns, which gets fed into an analytics cluster. You would then have a read replica on which you verify that your data is appropriately encrypted, and if it is not encrypted, it doesn't contain PII. You would make sure that your database stores its data in an encrypted fashion. And additionally, you would add things like app-based, key-based encryption or anonymization, depending on your use case. So that's all we had for this iteration of how to do a distributed database architecture for GDPR. Hope you guys enjoyed it. Hope it was informative. Reach out if you guys have more questions, and do give Yugabyte a try. You can do so from our docs from the Quick Start. Thank you.